today's lecture on section 7.1 and 7.2, functions of two variables and partial derivatives. So we'll talk first about section 7.1, function of two variables. Then we'll talk about section 7.2, partial derivatives. Let's begin with x and y being two variables. You've seen that before, but you're used to seeing x as being the independent variable, or the input, and y as being the dependent variable, or the output. F of x comma y is a function of two variables. It takes two variables, x and y, as inputs now, and returns one output. So if f of x comma y is a function of two variables, it will take two variables as inputs and return one number as an output. Here's an example. Let's say x is the number of cars sold, y is the number of mopeds sold, and f of x comma y is the profit obtained. So company sells x many cars, y many mopeds, and gets a profit of f of x comma y. Example 2, let's say x is the number of miles east of Honolulu, y is the number of miles north, and f of x comma y is the height above the ground of sea level. So if we drew up a diagram here, we have here's east, here's north. The center here would be the town of Honolulu, and around here, over each point, you can imagine a height. And f of x comma y would represent the height above sea level. Now, an important topic for functions of two variables are level curves. Level curves are defined as follows. We have a function of two variables, f of x comma y. C is a constant. The curve f of x comma y is equal to c is called a level curve or contour line of the function. Let x be the number of miles east of Honolulu, y being the number of miles north, as before. F of x comma y is the height above ground, above sea level. And the level curve here, or contour line, will give all places around Honolulu that are of a height c above sea level. So if we drew this diagram again, we have east, north. This contour line here would represent all places, say, that are 10 feet above sea level. And these are important because they're used in topographic maps to show regions in an area that have the same height. So when you look at a map, you're not going to usually get a three-dimensional map. You're just going to look at a map on a piece of paper. It's two-dimensional, but how does it represent the region? Well, a region has number of miles east of a given city, say Honolulu. It also has the number of miles north of a city, and at each of those locations, there's also the height. So topographic maps and contour lines are used in topographic maps to show that extra dimension of height. Here's an example. So down here we have a topographic map in this two-dimensional paper. And as you can see, each of these are contour lines. 1100, 1200, 1300. These represent the height of this contour line above sea level. So all these places on this contour line that corresponds to 1100 are, say, 1100 feet above sea level. And if we go up here, you can see it's this curve here on this surface. And you can use this topographic map can be used to reconstruct this three-dimensional hilly region. So what's really going on here? Well, outside we are at say around, let's say this was around sea level, so that's say 0 feet. We go in a little bit, okay, then we get to a region, this curve around here, that's at a height of 1100 feet above sea level. So we said before, it corresponds to the curve up here. Then here we get to 1200 feet above sea level. So we're in even a narrow region that is 1200 feet above sea level. We go further in, closer to The top of the mountain, well, now we're at 1,300 feet above sea level. We keep going further in, well, now we're at, say, 1,400 feet. And as we can see, it's not listed exactly what these heights are, but this contour line corresponds to the region around here. This one peak, that's actually a local maximum, two-dimensional local maximum. And the second peak here, it's another local maximum. There's also a local maximum up here, and that corresponds to this contour line right here. All of the places on this contour line have the same height above sea level. Okay, so there you have it. That's how, even though this is drawn on a piece of paper, a two-dimensional plane, it can be used to reconstruct this three-dimensional surface. That's what contour lines are used for. Contour lines, or they're also called level curves. Here's an example for determining the level curves. Let our function be x squared plus y squared. Determine the level curves of f. Notice that f can never be negative, since x squared plus y squared is always larger than or equal to 0. It's 0 only if x and y are both equal to 0. If we pick any positive number, then the level curve x squared plus y squared is equal to c. What is this? This is a circle in the xy plane of radius square root of c. And what we conclude is that level curves of f of x comma y are indeed circles. So if we were to draw them, start when c is 0, that would just be the point 0, degenerate circle. Then larger and larger circles for larger and larger values. Let's see. That's what's going on there. So these would be all the contour lines. This would say c is equal to 10. Here and here would be c is equal to, say, 5. Now we're going to go to the next topic, which is partial derivatives. We're going to find them. f of x comma y is a function of two variables. Consider the point a, b in the xy plane. This just means x, the first input has the value a, the second input y has the value b. The partial derivative of f of xy with respect to x at the point a comma b is equal to this limit. Notice how in this case, you're only adding h to the first input, not the second input. The second input is held constant at b. Likewise, the partial derivative of f of xy with respect to y at ab is this limit. Notice here the first input is held constant. The second input, you add h, and you subtract the value of the output at ab divided by h. What this means is that the derivative of f with respect to x at ab, the partial derivative, so notice in this case the notation here, you write partial, it looks like a backwards e instead of the d, it's for partial, measures the rate at which the output changes with respect to the first input, while the second input is kept constant. When the first input is at a and the second input is at b. So this last clause here is just saying, well, at what point do we consider? What inputs are we considering? And here we're saying, well, what is this measuring? This partial is measuring the rate at which the output is changing with respect to the first input. Second input is kept constant. Likewise, partial f, partial y at AB measures the rate at which the output f changes with respect to the second input. First input, of course, is kept constant. And again, when we're at first input is at A and second input is at B. Here are the steps to compute df dx of A comma B, or partial f, partial x at A comma B. You treat y as a constant and differentiate f of x comma y with respect to x. So notice if we're given a function of two variables and y is constant, f of x, or let's say it was just f of x comma b, that's a function of x. That's a function of x only. You can differentiate it with respect to x, and then plug in x is equal to a. Likewise, to compute df dy at ab, treat x as a constant and differentiate f of x comma y with respect to y. Notice if you replace the first input with a, this is a function, f of ay is a function of y, differentiate it, plug in x is equal to a, and voila, you got the derivative of f with respect to y at input level a and input level b. So first input is a, second input is b. Let's see how this plays out in an example. F of x comma y is x squared times y plus 2xy plus y cubed. Our job is to compute partial f partial x at 1, negative 1, and partial f partial y at 1, negative 1. To find partial f partial x at 1, negative 1, here's what we have to do. We differentiate this function with respect to x by treating y as a constant. X squared y plus 2xy plus y cubed. Notice if y is constant, this last term is just constant, so its derivative is 0. That's why there's really 0 out here. 0 plus anything is itself. Now the derivative of x squared times y is a constant, so we can just pull it out. Derivative of x squared is 2x. That's why this corresponds to this term. Derivative of x squared y with respect to x is 2xy. Now, the derivative of 2xy is equal to 2y because we can just pull out x. The derivative of 2y times x, of course, is just 2y. The derivative of any constant multiple of x is that constant. Now we're going to just plug in. Next step is straightforward. We just plug in x is 1, y is negative 1. When x is 1 and y is negative 1, this first term is 2 times 1 times negative 1. We add 2 times negative 1. Negative 2, negative 2, negative 4. To find df dy at 1, negative 1, differentiate the function with respect to y by treating x as a constant. Df dy is equal to x squared. So here y is a constant. Here x is a constant. So we're differentiating x squared times y with respect to x. X squared is a constant. We pull out x, derivative of any constant, multiple of y with respect to y is that constant. So derivative of x squared y with respect to y, of course, is x squared. The derivative of 2xy with respect to y, likewise, is 2x. Derivative of y cubed is just the power rule, it's 3y squared. 3 comes down, subtract 1 from the power, and it becomes 3 minus 1, which is equal to 2. Next, plug in x is 1, y is negative 1. We get df dy at 1, negative 1. It's 1 squared plus 2 times 1 plus 3 times negative 1 squared. X is 1, and y is negative 1. Everything's positive here, so it becomes 1 plus 2, which is 3, plus 3, which is positive 6. Okay, there you have it. We computed the first partials. Now, there's also something called second partials. So notice from the last example, both df dx and df dy are functions of x and y. When you differentiate the function f of x and y with respect to x, you get another function of x and y. When you differentiate the function f with respect to y, you get a function of x and y. We can differentiate these functions with respect to x or y to get the second partials. d dx of df dx is d squared f dx squared. d dx, or the derivative of df dy with respect to x is equal to d squared f dx dy, or, okay, there should not have been an f there. It should have been d dy, the partial of df dx with respect to y is equal to d squared f over dy dx. Now these are called the mixed partials because you're differentiating first with respect to x, then with respect to y, or vice versa. First with respect to y, and then with respect to x. And of course, if we differentiate first with respect to y, and then with respect to y again, we get d squared f over dy squared, second partial of f with respect to y. Let's see how this plays out in an example. Function is the same function we had previously, x squared y plus 2xy plus y cubed. We're going to compute the first partials, df dx, and df dy, as well as the second partials, d squared f dx squared, d squared f dy squared, and d squared f. This should have just been the mixed partial dx dy. We've already found the first partials, df dx, is 2xy plus 2y, and the second partial, df dy, is x squared plus 2x plus 3y squared. So, d squared f dx squared is d dx, the partial with respect to x of df dx, which is the partial with respect to x of 2xy plus 2y. Now, when we differentiate 2xy plus 2y with respect to x, we are treating x as a constant. That means the derivative of 2y is going to be 0. The derivative of 2xy, of course, is just 2y because we can pull out the x. The second partial with respect to y, we found before, the first partial with respect to y is x squared plus 2x plus 3y squared. So we differentiate that again with respect to y to get what? Derivative of x squared is 0, derivative of 2x is 0, derivative of 3x squared, y squared is equal to 6y. So there you have it. The mixed partial now can be computed in either order. We can either differentiate with respect to y first, then differentiate with respect to x, or differentiate with respect to x first, and then with respect to y. d squared f dx dy is equal to partial with respect to x of df dy, which is equal to the partial with respect to x of x squared plus 2x plus 3y squared. Here we treat 3y squared as a constant because we're treating y as constant when we differentiate with respect to x. We differentiate each of these terms just by, as we would normally any polynomial. Derivative of x squared is 2x, derivative of 2x is 2. So we get 2x plus 2. Derivative of f with respect to y, then with, or we can do it the other way. First differentiate f with respect to x, then differentiate f, then differentiate with respect to y. Derivative of f with respect to x is 2xy plus 2y, which is equal to 2x plus 2. Because here, x is a constant, we can pull this out, we're left with 2y. Derivative of 2y with respect to y is equal to 2. There you have it. And that's how we compute both first and second partial derivatives. Okay, so I'll be uploading another lecture that'll be on how the first and second partial derivatives can be used to determine whether or not a critical point, we'll talk about that later in that lecture as well, can be used to determine whether or not a critical point is indeed a local maxima or local minima of a function of two variables.